So today we're going to look at higher derivatives, the second derivative, third derivative, and you can do more and more derivatives. So we have notations for the second derivative. You have f double prime or y double prime, just adding another dash up there. And in Leibniz notation, we've got d2y over dx squared. And all it is once you've done the first derivative, you take the derivative again. So it's really nothing crazy new. We just have to get used to some new notation and some new ideas, but the actual process and working through it is not bad. All we're going to do is we're going to find the first derivative, and then once we've found our first derivative, we might manipulate that equation, simplify it a bit, and then find the derivative again.
Can you go back to that?
Yeah, I can go back for a second. So it's important to take the time and say what's going to be the easiest thing to do multiple derivatives of. And this is something that I noticed on your quizzes. Sometimes we didn't take the time to do it. For example, this 5 over x that we see, a number of you on your quizzes use the quotient rule. That's not wrong because you have a function divided by another function, and it will give you the right answer. It's just a lot more work than doing the power rule, because that first one, x cubed, is really easy to do the derivative of. And if we could rewrite this as 5x to the negative 1, then that's going to give us two power rules, which are the easiest ones to do, rather than a power rule and a quotient rule. And when you do a quotient rule, you get something big, and if you get something big and you have to do a derivative again, it's just going to get even bigger and more complicated. So if we can change things first to the simplest form that we can do the derivative of, it's going to make our life easier. So now we can find our first derivative. By bringing that exponent out in front and subtracting 1 from the exponent. And now everything is still in the power rules, so finding the derivative again isn't too bad. And if you want to find the third derivative, you could go again and again and again. You could probably even, this one wouldn't be too hard to figure out the pattern and write out what the nth derivative looks like. Yes? Yeah, the negative 1 came out in front, making it plus 5. Right? Because negative 1 times negative 5 is plus 5, and then I subtracted 1 from the exponent. Here's just different notation. Here's Leibniz notation. It's asking the same thing. What do we have in the first derivative here? What kind of rules are we going to have? We're going to have the chain rule. So dy dx, 3 is going to come out in front. Inside stays the same. Subtract 1 from the exponent. Multiplied by the derivative of the inside, 2x minus 3. Now what are we going to have when we do the derivative again? Chain rule and product rule. Right? So here's our product. Here's one function multiplied by another function. So to do our second derivative, keep one the same, multiplied by the derivative of the second one, plus keep the second one the same, multiplied by the derivative of the first one, chain rule again, bring the 2 out in front, subtract 1 from the exponent, multiply. Which 2? From here, I brought this 2 out in front to get that 6.
At the very start, could you just apply the power of 3 to both?
Yes, so now here you have to say, does it make more sense for me to multiply this out completely, either using my binomial theorem or just expanding it, because that would make my derivative easier to do later on. So I had to do more work from step 2 to step 3 because I didn't simplify to begin with. But if I would have taken this originally and multiplied it out, what am I going to get? Well, it's to the power of 3. So if we think about, do you want to use binomial theorem or do you want to use Pascal's triangle to expand it? What would be, or do you want to just expand it old-fashioned way where you multiply 2 first and then multiply the third one? Old-fashioned way? So old-fashioned way, you would have x squared minus 3x 3 times. We could take the x out, but we're going to have to multiply it in afterwards anyways. So we're going to get x to the 4 minus 6x cubed plus 9x squared. Because you're going to get, when you do the outside, you're going to get minus 3x cubed, another minus 3x cubed. I just combine them right away. I still have x squared plus 3 minus 3x here. Yes?
I thought that the 3 method applied to both terms. So it should just be x6 minus 3x.
No, you have to. So that's true if you're multiplying. So if you had x squared times a negative 3y all cubed, then when you write it out 3 times, it's all multiplication, so then the cubed applies to both. But whenever there's an adding or subtracting in there, you're going to have to expand and distribute and think about all the arrows that would happen. So now this next one's going to get even bigger, right? We're going to get an x to the 6. I'm going to get an x to the 5 this way and an x to the 5 this way. That's going to give me minus 9x to the 5. I'm going to get an x to the 4 here, so 9 of them, plus 18 of them, plus 27x to the 4. I'm going to get an x cubed here, so minus 27x cubed. Barring any mental math mistakes in there, which there probably is one, this would be our function. And now taking the first derivative would be easy. And then taking the second derivative would be easy, and the third derivative. So depending on what you're going to need to do with the function, maybe it makes sense to expand it like this to begin with, because now we've got just the power rules to deal with, and the derivatives are going to be really easy. So depending on how your textbook's answer looks like, you might decide to do one way or the other. The important thing, though, is that you're thinking about that all the time. And it's one thing, again, from your quizzes, I noticed a lot of times on ones like this, you didn't make that decision, should I use quotient rule or should I change it first? You should always be thinking about those things and just sort of, in your mind, see how much work is both going to be. And then when you realize, oh, one way is going to be less work, it makes sense to change this 5 over x to 5x to the minus 1 to begin with, because it's going to save me time later on, then that's worth doing. Now I'm going to just make up one more just for fun. Let's do just to connect it to what we were doing before. That looks like fun. Whew, implicit differentiation and the second derivative. So first, yeah. Oh yes, thank you. Now, as far as this notation, the d2y over dx squared comes from, it's because we're doing the derivative twice. And so this means take the derivative once. This means take the derivative again of y. That's basically what we're doing. So on the top, you see that the two d's sort of go together. That's why the d squared is between the d and the y. And on the bottom, you have dx twice. So technically, there maybe should be nice brackets around that to show that the dx happens twice. Although mathematicians don't like brackets, and they often think of ways to get around not having brackets. And so it was just agreed upon, I think, it's my idea here, that if we just write it as d squared over dx squared, people will know what we mean. Or maybe they're thinking that dx itself is one thing, so it doesn't need brackets, because it's not separated. Just like, you know, you never have to write sine in brackets so that everybody knows that those aren't three different individual variables multiplied together. You just know that that means sine. Who knows? Okay, anyways. So here we have this implicit differentiation. On the left side, do you see that you have the product rule? And the product is right here. One function is 3y, the other function is x. So we keep the first one the same, derivative of the second one, which is just 1, plus keep the second one the same, derivative of the first one will be 3, and then the derivative of y, dy dx. And derivative of the right side is going to be a chain rule. Outside function is the exponent, so 3 comes in front, subtract 1 from the exponent. Derivative of the inside function, which is y, is just dy dx. So if we take all the ones that have dy dx and bring them to one side, and all the other ones and bring them to the other side, we can factor out a dy dx. Now, when I made this question, I had no idea how long it would be. So now we've found our first derivative. Now we have to do the derivative again. What's going to happen? Well, the nice thing is when we do the derivative again, this side is just going to be the second derivative. This side, we're going to have some work to do. Yes, we're going to have the quotient rule and implicit differentiation. So we keep the bottom the same, times by the derivative of the top. And the derivative of the top is going to be negative 3 dy dx minus, keep the top the same, derivative of the bottom, which will be 3 minus 3 minus 6y dy dx all over the bottom squared. So there's the second derivative. If you wanted the second derivative without the first derivative showing, and we're not going to actually do this, but you see where this dy dx is? And you see that it's again here? You could substitute this in at those places. Okay? And then you could look at the back of the book and try to simplify it to whatever they came up with. But we're going to leave it like this for now. Okay? But there's the idea. So once you find the first derivative, you just do the derivative again, and it doesn't matter how complicated you had to start with, right? Can you imagine trying to find the third derivative? We'd have the quotient rule again, And within the quotient rule, we'd have the product rule. Yeah. And if we substituted this back in, yeah. Yeah, it's like a little nightmare. Sorry for hopefully. Yeah. So there's some questions for the second derivative.